Hi, I'm Kurran Singh. I'm a fourth-year PhD student in Professor John Leonard's Marine Robotics group, and my research focuses on underwater localization and mapping, so how we can build a map underwater and how we can figure out where the robot is underwater. One research project in particular that I've been working on recently that I'm excited about is underwater mapping for kelp farms. So kelp is an important part of potentially a battle against climate change. It ends up being a major storer of carbon, and it's also very useful for things like eventually textile manufacturing and even food. So part of this project is how we can use robots to inspect these large kelp farms and make sure everything's healthy, everything is tied off where it should be, nothing is rusting out. And we want to be able to do this autonomously. Currently, this is done with human operators going through and checking everything by hand. But if we could do this with a robot, then it would be much more repeatable and efficient to be able to do that way. Currently, we have a test vehicle known as a Blue RV, which is relatively cheap and easy to deploy. 1 or 2 people can carry it around and throw it in the water on their own. So we don't need any cranes or large ships to operate this vehicle, which is really nice. And we have a lot of the sort of algorithmic fundamentals in place and the software infrastructure in place to collect this data and try and process it into a unified map. I think the next steps are to continue to improve the results of that software infrastructure on one hand, and then on the other hand, on the hardware side of things, to try and lower the cost. So right now we're using 2 fairly nice sonars. If we could use a single sonar, for example, that would be preferable. We're using a Doppler velocity log, which is very expensive, but if we could use other techniques that would reduce the cost of the vehicle further, such as sort of acoustic beacons or something along those lines, then that would also be desirable. And it's a tethered robot, so eventually this would be an untethered robot, but for now this is a good way to get real-time feedback as we're operating the vehicle in these areas. The next steps, hopefully, would be able to deploy this robot at a real kelp farm or a real aquaculture farm, such as like an oyster farm in the area. And then separately, actually, a class that I'm in here, I'm working with medical data that's deformable. So you can imagine taking scans of someone's hearts, and at different times, the heart will be a slightly different shape as it expands and contracts. And so that makes it tricky to actually align maps that you take at different times. And then I realized that this is actually very similar to the challenges that we would face with something like a kelp farm, where you can imagine these large seaweed leaves essentially swaying back and forth. So at different times, it'll appear different. And so it's tricky, and there's a lot of interesting algorithmic challenges that we can take from that medical application and try and apply here on kelp farms. There's a lot of differences in when you're writing an algorithm for something that could be in a repeatable environment like a factory or a house, versus if you're throwing these robots out into the wild in underwater situations, or even just potentially out in nature versus somewhere man-made. And so I think one of those, the main algorithmic difference is that with what we call a prior map, you're essentially taking observations of the world and trying to align those with something that you already know is there. So if you see this building and you know there's 4 buildings on the street, you might try and figure out which building it is. If you haven't seen this environment before, or it's a totally new environment and it's changed from before, you don't have the ability to align this with a previous map. You're just building the map on the fly while also trying to figure out where you are. A lot of people will be familiar with how object detection works in the air. So for example, you can point camera at a chair and it'll say that's a chair. It's not as simple as just applying those models underwater though, because camera data is very difficult to obtain and use underwater. A lot of the time it's too turbid, there's mud kicked up, or there's not enough light to actually use camera data to recognize these objects. And furthermore, even if we did have good camera data, there aren't a lot of data sets to train these object detectors on. So one of the key reasons that these in-air object detectors have become so successful is that there's just tons and tons of data out there. These big tech companies are able to scrape basically the entire internet to train these models at this point. But there isn't that level of data for underwater applications yet. So that's one challenge. The other challenge is that we actually often can't even use camera data. So we have to use, like I'd mentioned earlier, sonar data, which is inherently noisier and has several limitations compared to camera data. So we don't have color information with sonar, we just have the distance to that point, the angle to that point, and then the intensity of that return. So that's much trickier than having the exact color and exact point in space of where an object is. And so part of the focus of what I'd like to do with the rest of my research is to potentially start with camera data and use some of the existing, if limited, data sets to train up an object detector for underwater data, and then to use that camera object detector to then train an object detector for sonar, and to try and improve the state of the art that way, and to be able to have sonar object detectors that reliably work in a variety of environments.